You know, whether it's a self-driving car trying to get across town or a little robot zipping around a warehouse, the basic challenge is always the same. How does it get from point A to point B? It sounds so simple, right? But solving this A to B problem is actually one of the most fascinating puzzles in all of artificial intelligence.
When we think about this stuff, our minds usually jump straight to the hardware. We picture all the cameras, the radar, the LiDAR spinning on the roof, all that tech that lets a machine see the world. But honestly, that's just the beginning.
And here's the thing. Seeing the world, that's kind of the solved part. The real trick, the absolute magic, is what happens next. It's the decision. Once an AI has a picture of its surroundings, how does it figure out the perfect, safest, most efficient path to take? That's the heart of the A to B problem.
Okay, so let's start with the most classic way to solve this. The idea is to take the messy, complicated real world and turn it into something clean and logical, like a giant map. Think of it like a digital game of connect the dots, where the AI just has to find the best way through the maze.
This whole method is called graph search. So imagine every possible intersection is a node, a single dot on the map, and every street is a line connecting those dots. The AI's job is basically just to explore this huge, sprawling web and figure out the absolute best path from its starting dot to its destination dot.
Now, the most famous of these graph search methods is called the A-star algorithm. And what makes it so brilliant is this one little trick. It doesn't just look at how far it's already gone, it also makes a really smart guess, what engineers call a heuristic, about how much distance is left to the goal. By combining what it knows for sure with an educated guess about the future, it stops itself from wasting time on paths that are obviously going the wrong way.
But A-star isn't the only game in town. See, it's all about trade-offs. You've got simpler methods that are really fast but might miss the best route. Then you have something like Dijkstra's algorithm, which is super careful and will always find the perfect path, but man, it can be slow. A-star kind of hits that sweet spot of being fast and optimal, but only if its guess is a good one. This is a huge theme in AI pathfinding. There's almost never one perfect solution, just the right tool for the job.
So that's the super mathematical, logical way to do it. But what if the best solutions aren't in a textbook? What if they're outside, in the wild? Turns out some of the most clever pathfinding algorithms come from a place you might not expect, the natural world.
Just look at these two incredible ideas, both inspired by nature. On the left, you've got ant colony optimization. Digital ants explore the map and leave a virtual pheromone trail. Shorter paths get traveled more often, so the scent gets stronger and attracts more ants, and pretty soon the best route just sort of emerges from the crowd. Then, on the right, you've got particle swarm optimization, which is basically like a flock of birds. Each bird knows its own personal best spot, but it also knows where the group's best spot is. And by constantly adjusting its path based on both, the whole flock eventually swoops in on the perfect solution together.
And believe me, it does not stop with ants and birds. Researchers have created algorithms based on how gray wolves hunt in packs, how bats use echolocation, how bees forage for nectar, even how our own immune systems adapt to fight disease. It is a whole digital zoo, all working on the same A to B problem. How cool is that?
All right, let's switch gears completely. We've done math, we've done biology. What if we just use the basic laws of physics to guide our robot? What if we could create a path out of invisible forces?
Well, this is the idea behind the artificial potential field method, and it is just so elegant. Imagine your destination is a giant magnet, pulling the robot towards it with a powerful attractive force. At the same time, every single obstacle is also a magnet, but it's pushing the robot away with a repulsive force. The robot doesn't even need a map. It just follows the path of least resistance created by all this pushing and pulling.
It sounds foolproof, doesn't it? Just follow the forces. But there's a famous catch. What happens if the robot gets into a spot, say a dead end, where the forces pulling it forward is perfectly canceled out by the forces pushing it back?
Yep, it gets stuck. It's in what's called a local minimum. It literally can't move without temporarily going uphill against the forces around it. And this one single problem is the reason why there are dozens and dozens of improved APF algorithms out there. Each one is just a clever little trick, a virtual nudge or a random jiggle designed for one reason, to help the robot get unstuck from these invisible traps.
Okay, this brings us to the final frontier, the really cutting-edge stuff. So far, everything we've looked at has been about following rules, whether they're mathematical, biological, or physical. But what if the AI didn't need any pre-programmed rules at all? What if it could learn the best path all by itself, from scratch, just from experience?
Well, welcome to the world of reinforcement learning. The easiest way to think about this is like training a puppy. When the AI makes a good move, like getting closer to its goal without hitting anything, it gets a virtual treat, a reward. If it makes a bad move, like bumping into a wall, it gets a penalty. You let it do this millions of times, and eventually it figures out a strategy, a policy, that gets it the most treats possible. It literally teaches itself.
So today, the really advanced systems aren't just picking one of these methods. Nope, they're creating a cocktail of all of them. They use things like deep Q networks to learn strategies in crazy complex environments. They use imitation learning, where an AI basically just learns by watching a human expert do the task. And now even large language models are getting in on the action, helping an AI use general knowledge about the world to make smarter decisions. Like, figuring out that sidewalks are for people, not for cars.
So there you have it. 4 totally different philosophies for solving the exact same problem. We've got the meticulous map searchers, the clever mimics from the natural world, the elegant physics-based navigators, and now intelligent systems that literally learn on their own. It's a pretty amazing evolution of ideas, right?
Each one of these approaches is a huge leap forward, getting us closer and closer to machines that can navigate our world just as well as we can. But it leaves us with one final, fascinating question to think about. See, so far we've only been talking about how one AI finds its path. What happens when our roads, our skies, and our warehouses are filled with millions of them, all solving their own A to B problems, all at the same time? That is the next great puzzle for AI to solve.